Hi, Professor. Can I talk to you about my project?
Yes.
I'm not sure if you got my emails from the past week or so, but last Sunday, I emailed you about the feedback that you gave me. You
Yeah.
were asking me how it relates to a programming language. So I was a little confused about that feedback.
Okay. Our definition is very simple.
Uh-huh.
Anything related to programming language course will be okay. So
Uh-huh.
basically, what is programming language mechanism? It's just anything you translate from one language to the other will be acceptable. That is not
Okay.
very confusing. That is very clear.
Yeah.
Yeah.
So would me creating a web app with different APIs and
So
stuff, would that
where
not
where is the translation? My question is, where is the translation?
uh-huh.
Yeah. You have
The
to ask yourself.
translation.
Yeah. Do you
Um,
translate one language to the other?
uh-huh.
Yes or no?
I was thinking of taking the JSON data and trying to like visualize the data as well. Like try to plot the points on some
Yeah,
map
in
after
that
the
case,
fact or
that's okay. You translate from your JSON to a say let's assume that you translate from a JSON to a geometrical, say JSON is like something like this, right? You have
yeah.
some
Uh-huh.
A3, whatever. Okay. You
Yeah.
translate to something like this, that's okay.
Yeah, but that wasn't the core idea of my project, but I see what you're saying. I was also gonna try to take the JSON data and try to like train it with machine learning data. Would that be also like in the realm of programming
I
languages, or do you think?
don't care about the machine learning part, but you translate to
Yeah.
something else that would be acceptable.
Okay.
Machine learning
And
is a different story. You like to
yeah.
implement something for machine learning, that's fine.
Yeah.
But key point is that we are a class teaching programming language, and we teach you like this different type of the scanner or context-free grammar converter or
Yeah.
parser. You have to
Uh-huh.
apply this knowledge to your project. That's what we say.
Okay.
Yeah.
And since you're saying this, is it possible for me to switch my project to do the JSON, the GeoJSON thing?
Whatever project is okay. Proposal is one thing. I emphasize it many times.
Yeah.
Proposal is to try your idea, try to propose to other people. In the middle, if you want to switch topic, it's okay.
Oh, okay. So I don't need to make a new proposal for you to review,
No,
or I can
no,
just go
no,
ahead and
no.
start it?
Yeah, you can start with a different project.
Oh,
But
okay.
the project must be related to programming language mechanism.
Yes.
Okay.
Yes. Okay.
Anything related to that will be acceptable. This we make it very clear. We don't
Okay.
want students to bring in the project from other courses or anything else.
Yeah.
Okay. That's the key.
Okay.
Okay. So
Okay.
if the project is irrelevant to the course, it will not be acceptable. Other than that, if you do any kind of translation, will be acceptable. Okay.
I know in the beginning also, you also mentioned that we can use like NLP and stuff too. Would that be acceptable with programming languages? Because I know
Whatever
you.
you translate,
Okay.
whatever you have a translation, that will be acceptable.
Okay. All
So
right.
in the NLP natural language processing case, if you
Uh-huh.
translate from say from Italian to Portuguese, that's actually acceptable. If
Okay.
you are able to do that, okay,
Yeah. All right.
okay,
Thank you.
that's just an example. Okay, any more question? Anybody has more question? Okay, this session is supposed to be handling the any question in the project or assignment. Okay, we are emphasizing on there. So if you have any question, let me know. Okay, we are actually past the noon time, but any questions so far other than Nayo's problem? Okay, any question? I'll try to handle the question first. No? Hello?
I've got
Any-
no
No.
questions.
Yes, go ahead.
I said I have no questions.
You have no question. Okay.
Yeah.
So anybody has question? Okay, no question. I'll go over the overview for the lecture 12. Okay. So basically, last time we spent more time on focus on the what on the lecture. So we actually try to teach you. Okay. So we try to teach you how to generate a lecture. Okay. So to generate a lecture, there are two ways we can do it. One is ad hoc programming. So you actually knowing about a finance state machine, and then you kind of handcraft the finance state machine. Okay, that's one way we call it ad hoc solution. Okay, ad hoc. Okay, ad hoc scanner design. Okay. And last week we talked about a different one that actually is designing using the regular expression and then feed into a Flex, okay, program, and then generate the lexical analyzer. Okay. So this week we are on here trying to look at the parser. Okay. Trying to look at the parser, and we also want to make sure that it actually is robust and can be generated by the systematical way, okay, by a machine-driven way, okay. So that's using the Python, okay, using the Python. So one thing we need to know is actually parser is the heart of the compiler, okay. So okay, so we do language translation, right? So the lecturer's job, okay, the lecturer's job, okay, or scanner's job is doing this, okay. Okay, so it translates to, it actually created a token stream, I, and then N, Y, okay. And then this one really go into the parser, right? So parser want to see is actually, this is actually a subject, okay, verb, okay, and then object. And then this is a sentence, okay. And subject, you have I, that's a token. M is here. Okay, and object is here. It actually is, I'm sorry, it's not object, okay. I'm sorry, I make a mistake. This one is not object. Find actually is a verb, okay. I think right here it is an adjective. It's describing a person, okay. So this is adjective. Okay, that's actually this one is fine. Okay, so actually you create a parser, right? And you actually create a syntax tree. So this one we call the syntax tree, right? And this is in the syntax tree will actually eventually generate some code based on this, right? So basically this one, we do have the syntax tree. And the next stage is code generation, right? So actually next stage, you pass the syntax tree to code generation. So let's assume that we are translating this I'm fine to Japanese, right? Okay, so basically one thing is Japanese language structure is actually it will be subject, okay, and then actually there's no verb in here, okay, and then actually it is adjective, okay. So basically it actually only this. There's no verb, okay. So basically in Japanese it will be translated to I will be translated to watashi, right? Okay. And then there's no verb, but it will actually it has a kind of special special as a verb type. Okay, so it would be watashi wa, but this one is not a verb. Okay, and fine is daijoubu. Okay, so daijoubu is. Okay, so it will be translated to that. So you will follow translate from a syntax tree to another syntax tree that actually is in different language. So you create a code generation. Okay, you create a code generation based on a new grammar. Okay, new grammar. So the whole process of language translation actually happened in the parsing stage and code generation. This one is just a supporting unit. Okay, the lexical analyzer is only a support. It just token out the language units. Okay, I is a word. It just token out word as the language unit. But the grammar translation part really happened on the parser and the code generation. Parser is analyzing your input tokens organization. Code generation is based on the output grammar to generate it. Okay, is that okay so far? Okay, that actually is what we want to have on the translation. So parser is the heart of the typical compiler. So if your parser design is wrong, no matter how good your scanner is, it is not going to do the translation you want. Okay. So parser call the scanner to obtain the token of the input program, assemble the token together to a syntax tree. So the main idea is to assemble the tokens to a syntax tree, okay, based on what we talk about, okay, and then pass the tree to the later phase. Later phase is code generation, okay, of the compiler, which performs semantic analysis and code generation and improvement, okay. So parser is in charge of the entire compilation. There are 6 stages, but this stage 2 parser will be the key element, okay. Okay, it's a syntax directed translation. So basically, you have 6 different stages. Parser is here. Okay, you create a syntax tree. And then the next one, semantic analysis, is also very important. But basically, this stage, most of the time, is to do a grammar check. So here you generate a certain tree, right? Syntax tree, but you have to pass the grammar check, okay? So basically this is what will happen. So here is parser, and then actually created syntax tree, and then actually here you have semantic analysis. So this semantic may happen when you do integer I equals 3.4. So you have a data type, you have a variable, you have a assignment, you have a token for the value, but this value is actually double type. So apparently this one has a grammatical error. So this stage is to check if this whole sentence, this whole statement, is actually acceptable in grammar or Java grammar or not. Okay, so this stage is to do that. But here you do create this the syntax tree before you go into the semantic analysis. Okay, but this one parser create this one, and semantic analysis will be decorating the syntax tree. So after the decoration, you generate semantic graph. Okay, instead of the syntax tree. So semantic graph is a decorated version of the syntax tree. Okay, and but still this one, I would say the main structure is still based on the syntax tree. Okay, still based on the syntax tree, but it's an AST with additional property and we resolve the reference. Okay, so here that means that the parser create the syntax tree, and then after that we still work on it to generate semantic graph. Okay, so this is the why parser is most important stage in compiler. Okay, so parsing, you really would actually put in the token coming in as a string. Okay, so you do have a string. So string is linear. Okay, linear, but it's a token string will be converted to a tree. Okay, So let's assume that we do have input of A times 2 plus 1. From our input file, it actually is an input string. But we really want to build a tree like this. Okay. So we need to actually find out each token's grammatical rule. Okay. So basically, A is an ID. Okay, so we do know this is ID, and then time is an operator. Okay, it's an operator, and then 2 is a integer value. Okay, so you will have the ID is value, and then this operator. Okay, called product. Okay, product. This one is a product operator. Okay, so basically this one is a value. So value time value. Okay, it becomes a product. Okay, so value time value time a product. Now this one plus is an operator. Again, it's an operator, sum operator. Okay, and then integer 1 is an integer and it's a value, and it actually is a vector. Okay, this one product, I think it means the product. Okay, so product is a vector plus another vector, which becomes a sum. Okay, so this is build up the tree. Okay, any questions so far? Okay, so to build up such a tree, we have to actually go through the process of having A is ID is a value is a vector. Okay, so you need to find this, and then this one this one is a integer is a value is also another vector. Okay, so you have vector times vector, so you actually okay, A you push into a stack. Okay, and then actually you are waiting for the star and another vector. Okay, and then you pop out this one to a tree. That is this vector 1 times vector 2. Okay, so here there is a parsing process that you push the grammatical unit into a step, and then once it actually matching certain grammatical expression for structure, then you pop it out to build a tree like this. Okay, and then you gradually build up the tree that will become your parsing tree. Okay, that will become its parsing tree. Okay, any question? Okay, so here we talk about parsing, but there are many ways to do parsing. One is bottom-up parsing. The other one is top-down parsing. Okay, so it's a LR parsing and LL parsing. Okay, we'll talk about a different parsing. Okay, but first thing is that you need to know about context-free grammar. Okay, that's the way that we describe our parser now, and then it's also called push-down automata. And push-down automata and context-free grammar both need to have a stack. Okay, both need to have a stack. You will have to build your syntax tree. You need to have a stack. Okay, whole stack. So you can process the tree construction. Okay, so they are simple. They are terminals. That those called tokens and non-terminal. Non-terminal are something like this one. So this one tokens are terminals. Non-terminal are these. These are non-terminals. Okay, sum or product. These are non-terminals. Okay. Okay, I'm sorry, I go the wrong way. And they are production and the derivation. Okay, these are two rules. Okay, to production is generate a large rule. Derivation is actually try to go over the tokens. Okay, and you create a parsing tree and sentential form. This one will be tested increase. Okay, you need to watch out this term. Okay, these are different terminology we are going to cover. Okay, so this one sentential form is the start symbol of a grammar or any string in the vertex union the terminal tree. Okay, which you can derive by the start. Okay, this one means that you have a start symbol S, and based on the terminal and non-terminal, this one actually terminal and non-terminal, vertex and the terminal, okay, 0 or more to generate from the start symbol based on the production and derivation rules, okay. So basically, concept grammar you actually create a production rule and derivation rules, and then you do have starting symbol, and you derive the so-called the vertex and terminals to match the production rule. Okay, this is a little bit too complicated. Okay, let's look at a simple example to describe this. So basically, let's assume that we do have a program, and that program is I equals 3. That's it. Okay, that's it. Let's assume this is very simple program. So program is a star symbol. Okay, program is the star symbol. So program actually may be defined as statements, okay, plus statements star. So it may be one statement and at least 0 or more statement. So program would be at least one statement and this one 0 or more statement. So this one is can be more statement. So statement can be defined as ID, okay, assigned with another value, okay, and then ID defined as what? We have a definition for ID, so it's later with followed by later or digit, okay, star. So that's actually ID. ID defines I, right? And then assignment. So assignment, next one is assignment. Assignment is a symbol equal. Okay, that's assignment. And then value. Value, let's assume is only natural numbers. So actually non-zero digit followed by digit star. Okay. And this is a set of grammar. This is a set of grammar. The starting symbol is this one called program. And everything else can be derived or produced based on the starting symbol. Okay, based on the starting symbol. So that is what we say the sentential form. Okay, sentential form means that the starting symbol can generate many forms, and what are the many different terms that can generate by the symbol is called sentential form. We'll look at these. Okay, we'll look at these. But so far, these are the theory. So sentential form is the starting symbol S of a grammar or anything generated by the symbol, acceptable symbols and terminals. Okay, so let's consider that we have SB, AB, S to this. Okay, these different rules. These are linear grammar. So we started with S. So S can be generating AS, AB, okay, AB, ABB, okay, ABBB, and ABB. So these different things that can be generated all by the S. So this whole thing is called a sentential form generated by S. Okay. And these are because S can be derived with AS based on this rule. Okay. And the second S can be generated by a B. Okay, so it can be A and B. So you can generate A, B. And this B can generate BB. So this can be the BB generated by B. Okay, and this B can be generated by BB. So that's another B. Okay, and the last B can be generated by a empty symbol. So this empty symbol is down here. Okay, so basically this tells us the rule that can, all of the symbol that can be generated by these grammar rules. Okay, and this whole set of all of the symbol or terminals that can be generated by S is called a sentential form of this simple S. Any question? Okay, so whatever, this is sentential form, okay? Okay, so passing by analog to regular expression to deterministic finite automata, its content-free grammar will be generating a content-free language, okay? And the parser is an order of 3 algorithm, okay? But this one is too slow. So usually we try to optimize the parser to become n log n time. Okay. If n3, that's too slow. Okay, actually too slow. So there is an infinite number of grammar for every content-free language. Okay. Okay, these are still very theoretical. Okay, so it turns out that content-free grammar can generate a parser that is n. It always can generate a parser with n over 3. Okay, time. But that's too slow. Okay, that's too slow. So there are 2 well-known parsing algorithms. One is called early algorithm. The other one is called CYK algorithm. Okay. Okay, but these are too slow. Okay, these are actually too slow. So nobody use the content-free grammar directly using the algorithm to generate it. Okay. Modern parsing don't do that. Okay. So there are 2 mostly used parsing style. That's not the CYK style. Okay, that's different one. We actually have the LL parsing and LR parsing. Okay, LL parsing means that it's going. Okay, here there's a comparison. LL parsing means the left to right parsing. Okay, and it will derive the when leftmost first. Okay. So LL means that it comes from left to right and leftmost deviation. Okay. LR parsing means that it's left to right scanning. So first thing is the scanning direction. Okay. The first L is a scanning direction. So scanning direction is going from left to right. Okay, that's called L. And the derivation is leftmost. Okay, it's called LL parsing. Okay, so it's in top-down shape. Okay, L right parsing is rightmost deviation. Okay, it's actually bottom-up deviation. How can we envision such LL and LR? Okay, so let me see. Wait. So how can we see LL and LR? Let's look at the assumption, okay? So let's assume that we do have something called list, okay? And we do have A comma B comma C, okay? So this one is actually ID followed by comma, ID, comma, okay, and ID, okay? And then we have, so list can be ID followed by another list, okay? And list can be a ID, okay? let's see, it can be a ID or empty string. Okay. Let's assume that ID can be ID or empty string. Okay, let's assume we do have this, right? And this one, A comma B comma C can be two-way. Can be ID followed by another sublist with ID, and then here you have comma, comma, and then here you have ID. Okay, there's another way that you do have ID followed by comma, and then ID, and then followed by comma ID. So this way is LL parsing. Okay, you create a grammatical union first, combined with later one. This one's left to right scaling, and that most deviation means that your this portion derived with a grammatical union first. Okay, if you are LR, passing still going this way, but rightmost will be deriving the grammatical union first. Okay, so that's the difference between LL passing and LR passing. So far, okay. Does that make sense? So one way is called LL passing. One way, the other way is called LR passing. Okay. So LL passing also called top-down passing, because you find you actually go depth first searching. Okay. You go down deeper, and then if there is a unit, you bring it. This one, no, this one you delay it. Okay. So because of that, LL parser and LL parser will have different way. When you write a program, it will be different. So LL usually is top down, LR is bottom up. Okay, and LL is predictive, and LL is predictive. LR is shift reduce. Okay, we'll see some example. Okay, when we do the parser, you will know why LL is actually top down and LR is bottom up. Okay. Anyway, so we do have LL and LR two-way. So LL is called top down or predictive parser, and LR is bottom up or called shift reduce parser. Okay. So but these actually have many different ways to do LL or LR, because that we want to beat the complexity of n's cube. Okay, we want to bring it down to n log n. Okay, so basically there are many style. Okay, many style of the parser. So there's one style called SLR. That's a simple LR parser. It's a type of parser with a small parsing table and a relative simple generator. So this one we do usually actually is what no look ahead. So this one zero look ahead, and then we have look ahead parser, LR parser. Now we'll look ahead one more symbol before you do passing. Okay, so there are different ones. So we have SLR parser and LALR parser, and there are many different parser, and the parser actually. Okay, let me show you the parser finally. Okay, let me try to find a slide to show you the parser finally. Actually, I cannot find the parser. Oh, right here. So basically, we do have different LL and LR parser. So we have LR zero look ahead parser, and LR one look ahead parser. Okay, and one look ahead two ahead, and there's a K look ahead parser. So if you look ahead more, your grammar will be more flexible and cover more content. Okay, but if you don't look ahead at all, then your grammar set will be smaller. Okay. And here is talking about LR parser actually usually is bigger than LL parser. Okay. So your LL parser's range covers range, like LL1 range is this much. The kind of sentence that you can cover is always smaller than LR1 parser. So LRK parser always bigger than LLK parser. Any question? No question? Okay, this is the comparison for L. But higher number of a K means that your grammar is wider, but your performance will be slower. Okay, so there's a trade-off. What if you increase the look ahead, then your grammar will be actually covering more sentence, but the performance will drop because you need to handle more things. So the content-free grammar actually is to find out a reasonable grammar set, okay, but allowing acceptable performance. Okay, that's the whole goal for designing a good parser. Okay, let's go back. Okay, let's go back. Okay, so we are in here. Okay, so there are top-down parser and the bottom top-down parser, bottom-down parser. So ID list is ID followed by a ID list tail. Okay, it can be comma ID and ID tail. Okay, so this one is passing your data such as ID, comma, ID, comma, ID. So your ID list is the ID with ID tail. Okay, ID list tail. So this ID list tail has a comma ID and then ID list tail. Okay, and ID list tail is ID list with ID, comma with ID, followed by ID list tail. But this ID list tail eventually followed by a semicolon. Okay, so this is actually a group of grammar, content-free grammar. Okay, this is a set of cover grammar, and this production rule can be passing using top-down and bottom-up parsers. Okay, so let's see how it works. Okay, so this is a set of grammar. And this set of grammar, if we use an LL parser, so ID list is ID list with ID and ID list tail. Okay, and ID list is ID list tail is comma ID with ID list tail. Okay, so something like this, you generate the whole, so the whole tendency of A, comma B, comma C semicolon is being passing in this way. Okay, so top-down parser begin by predicting the root of the tree, okay, and replaced by ID and ID list tail. Okay, so something like this one performing top-down parsing. Okay. Okay, next one. So next one is LR parsing. So LR parsing, you do start from ID. Okay, the first letter you see is ID. ID, and you see a comma. So ID with a comma, you cannot determine anything. So you continue to see another ID, and then with a comma and an ID, and then when you see the semicolon, when you see the semicolon, you know that this is ID tail. So ID tail and the ID, this one becoming another ID tail. So you form this ID tail, and then this ID tail with a comma ID, okay, it becomes another ID tail, and then comma ID, this ID tail preceded by a ID that form the first rule. So it actually creating the ID ID list. So here it has a top level ID list in there. This one is generation production rules. Okay, and that's why we call it. That's why we call it one. Shift and reduce. Shift and reduce. when you form a comma ID list, ID tail, ID tail. This scene create another ID tail. We call it reduce. So if from a sentence reduce to a non-terminal, we call it reduce. Okay. We call it this for LR parser. And then let's look at the LL parser. So the LL parser is, wait, where's our ID? LL parser is this one. LL parser is that you kind of look at the simple ID list. So ID is that go down to ID and ID tail. So this is top down. And we call it what? We call it predicted. So you need to predict this one. Okay. And you will see comma B. Okay. And this actually by prediction, it will be another ID tail. But at this moment, you do not see the ID tail. So you actually need to look at the two more symbol to determine it is actually ID tail. But sometimes it may be fail. If fail, you need to go back. Okay. So this one's top down and predicted. Okay. Okay, we'll look at the parser in more detail. But right here, this is the basic difference between the top down and bottom up parser using LR and LL parser. Okay. So there is a canonical delineation. At no point that the bottom up parser predict. Okay. And your top bottom up is always called shift reduce parser. Okay. And bottom-up parser is the first one to receive careful study. Rightmost deviation are sometimes called canonical. And in fact, most of the commercial compilers are LR style. Mostly are LR parsers. Commercial one, usually. Okay. Okay, so bounce the space with a grammar, bottom-up grammar. So bottom-up grammar, you may actually have a new set of grammar. You can redefine it in this way. Okay? But this one cannot be used to LL. Cannot, okay? Because there is a recursive code. There is it will create a recursive code, okay? There's a leftmost recursive, and that's not allowed in LL parser. Okay, so what it won't be say is LR parser may have different bottom-up grammar compared to LL parser. Okay, so here is still passing the A comma B comma C case, but the grammar is different. It's optimized for the bottom-up grammar. Okay. Okay, but anyway, here we don't go into the detail. It will generate a different style of the grammar. Okay. Okay, so they are LL1. Okay. Also LR1 parser. Okay. Rightmost recursion in the production. Okay. So when there's a one, that means the look ahead degree. Okay. The number means that. And when you have LR0, that means no look ahead. Okay, so LR1 means that it's actually a parser with one token look ahead. Okay, and if you have LR2, that means that two token look ahead. So more look ahead, your grammar rule will be more flexible. Okay, it cover more language. Okay, you commonly see LR, LLR, some number with a number in the parentheses something. The number indicates how many tokens you ahead. Okay, almost real compiler use one token look ahead. So most of the commercial one using look ahead of one. Okay, because of it will bring down the complexity of the compilation to n log n, but still cover enough grammar, okay, space. So the expression, okay, with the preceding and the associative, you see LR1, okay, but not LL1. Okay, so here let's actually have an example. So expression is a term or expression at operator expression. So this one means, this rule number one means you have an expression. So this expression can be a term, maybe three is an expression, or it can be expression at operational term. So it may be another expression. So maybe 3 plus 4 plus a term, that is 4. Okay. So term is actually a single number. Expression is an expression. Okay. And this expression plus a term can become an expression. Okay. So let's look at term. So the term is a factor. So a factor can be an ID number or a minus factor or expression. So this is a factor. So a factor can be x, can be 3, can be minus another factor, so minus x or minus 3, or can be a parenthesis with expression. And expression go back to the definition here. Okay. And add operator is plus minus. Multiply operator is time and division. So term, so you have 3 times 4 plus 4. This is the term. Okay. And this whole thing is an expression. So expression is a combination of a term. It either is a term or it actually is a plus minus sign, okay, operators. Okay, so here term is actually multiplicative. Expression is additive or subtractive. Okay, but so basically, expression is a higher order of the grammar. Okay, and term is a lower order, but term is usually under the expression. Okay, because this operator has lower precedence. Okay, when you look into the language. So this one define expression. Okay, it's 2.8 define any other expression. Any question? And this one be careful because there is a left recursion. Left recursion means that my definition, okay, it happened on the leftmost unit. That this grammar can only use LR parser, not LL. LL you create trouble. Okay, LL you create trouble. So this grammar can only be used for LR parser, but not LL parser because you have the leftmost recursion. Leftmost recursion means that term is defined by a term with something else, and that is you go back to term definition right away. So this is a recursive code, always recursive code. When there's a recursive, always a recursive code, LR parser doesn't work. Okay. Any question? Okay, let's look at. So basically, they are top-down parser and bottom-up parser. Okay? And bottom-up parser are using LR family grammar. Actually, top-down parser is using LL parser. So we will look into the LR parser first, and using recursive descent algorithm. Okay. And then we will go to here later. This one more suitable for ad hoc parser. This one LR parser more suitable for systematical parsing. So basically, all of the Python generated parser is LR style. Okay, not LL style. But anyway, we'll go into the detail for this. Okay. So first one, what we will see is the recursive descent parsing. So recursive descent parsing is for LL parsing. Okay. Okay, recursive descent is an 8-hop parser, and it's using the top-down grammar. Okay, so it's a LL1 parser. Let's assume that we are writing the LL1 parser for a simple calculator language. Okay, it's top-down parser, and the grammar is right here. And if you check it, there will be no left recursion. Okay. So if you check it, there's no left recursion. There's no turn defined by recursive call by itself on the first turn. We check that there's no, okay. Compared to the previous one, LR parsing. LR parsing's rule may actually allow some turn call itself first. This is okay in LR, but not okay in LL. So LL grammar never see that. Okay. LL grammar never see that. But based on this tool rule, okay, we actually derive a different set. Okay. Okay, let's look at this recursive descent parsing example. Let's assume we have terminal 2, okay, 1, 3, and terminal 9. Okay, so this is the grammar. So build a parsing of the mutual recursive one. Okay, so basically we have token string of terminal 2, T2, T5, T6, TA, and T9. Okay, so this is the token string. And we are trying to parse in this one from this token string to such a tree. Okay. Okay, let's assume this is a recursive descent example. So expression is turn or turn plus expression. And turn is integer or integer times turn or parenthesis integer. So let's assume that we have a simple input of, we see a token string of this. Okay, this is the program we have, okay. Very simple one. And there are 2 grammar. And we are going to do LL parsing using recursive descent parsing, okay. So let's look at how it works, okay. So start with the top level non-terminal. So we start with this one. Okay, we see this, but we start with the expression. We see this, okay, so we start with recursion here. Okay, so we do see a left side parenthesis. We see a left side parenthesis, so we try turn. And turn is here, okay. Turn is here. So we try turn. Okay. And then we try turn, we see a parenthesis. And you compare with integer, so it's 9 integer. So we do recursive call in it fail, you go back to turn. Okay, you try turn integer, but it fail. It doesn't match. So you go back to turn. So go back to turn, we try second possible turn. And it still fail because we see a parenthesis, we don't see integer. So you still fail, we go back. We go back and then we try next one. Parenthesis expression and parenthesis. So this is okay. This is okay. We look at the next symbol. Next symbol is int. Okay, we do the int. So int, we try a turn. So int, we try another expression. So go to this expression. An expression can be turn or turn plus expression. Okay. So we try turn. We try turn, and turn is an integer. So that match. So that match, you go back and try the parentheses. It's still matching. So match the inner input. So basically, we determine that this parenthesis int will have this passing tree. This is validated. Any question? Any question? So we go to try. Okay, if you go through this process, let's go back. I'm sorry, let me try to find the right page. If we look at this one, you do have a set of grammar. You do have an input. So based on your input, you try every grammar item one by one. Okay, and using recursive code, and it's called recursive descent. Recursive means that you actually try your leftmost recursively called depth first searching. That's called recursive descent. And once it fails, you go back. So that's recursive descent. Is that okay? Descent means that you keep trying the first turn first. And if the first turn doesn't work, you go back to try second turn. Second turn doesn't work, go back to try third turn. And if this one run out, you try different rule. Okay. But if match, you go back, return, and try second based on a second input token and try to match it. Okay. This is called
the second is term and expression.
Hmm?
The second one is term plus expression.
It's a turn, and a turn is another. So integer is a turn.
I mean, if it were moving past that,
and turn is an expression. Is that okay? Integer is a turn, and turn is an expression. When you backtrack it, integer is a turn, and turn is an expression. Is that okay?
Yeah, I was just saying if it failed that term, then you would go on.
If you fail that turn, then
term
you
plus
actually,
expression.
if you fail this turn as well, then the whole thing will create error. You just tell that this one, the program will have grammatical error. Compiler will compare it. Let's assume that actually you do have this, but you actually, the last one is a bracket instead of a curly brace, then this one fail. And totally fail. Totally fail, you'll report error in the grammar. Is it okay?
Mm-hmm.
If you try all three possibilities, fail, then this one doesn't work. You will try the second one. If the second one still fail, then you have grammatical error. Is that okay?
Yeah.
It doesn't mean that all the time your grammar, your input can always be valid. Sometimes you have error. So we have input string, and we will actually tokenize it into the words, and then we build a syntax tree. Okay, that's what we are doing. And here, this one is a recursive descent. It actually is a hardcore ad hoc parsing using LL grammar. Okay. So the problem with why here you cannot define expression and then expression with something, because if you call that the most possible will be recursive code all the way you cannot get out. Is that okay? So recursive descent cannot accept any of the term that's defined by itself with something else, because this one, if you do recursive descent, it's actually going to call it right away. This is infinite loop. It will be overflow. Is that okay? Stack overflow. So when we write the LL passing schema, there are certain rules you need to follow. Okay. Okay. Eventually, this will be creating some grammatical tree like this. Okay. Okay. Backtracking. When the syntax function fail, we want it to have no side effect. So you need to do backtracking. So backtracking means if you fail, okay. So first thing you try this. Okay. You try the different term. So once it fail, you need to clean up everything here, allowing a new evaluation. Is that okay? Let's go backtracking. Okay. Let's go backtracking. So once you actually doesn't pass, you need to allow it to recover or roll back to a certain condition to allow new trying. Is that okay? Allow a new try. This is called backtracking. So recursive descent code is going down and then trying, fail, go back. Going down, try, fail, back. Okay. It actually is something like that. So actually you just need to do recursive descent based on the recursive code and then got it. And if you don't do it, there's a table-driven way to do it. Okay. This is a systematic way to do it. So there are always two ways you can implement. Okay. But recursive descent is more straightforward without the table. If you use the table, then this one is more systematic way to do it. You require a stack to help it. Okay. And this one is called, we will use a table to process it. Okay. And using recursive procedure. So here you have, so recursive descent is a hop parser. Okay. And then this one with the passing table is a systematic way to do it. Okay. Let's see. Okay, so then we can write a recursive procedure for each terminal. So let's assume that we do have function called match. And we have program, and program is statement followed by terminal sign. So we write a program matching procedure here. Okay. And program will call the matching of the statement list. Okay, because you have a statement list followed by the terminal of the termination of the program. So once you call this you call program would actually call statement list checking and the data sign checking. So you would follow by two rules. And statement list will call this one. Okay. And it should be statement should be this one or this one or this one. Any of these three rules. Okay. And then your ID is, you verify if it comes with the ID. If it's not an ID, you pass. Okay. And expression will call expression here. Okay. Okay, it's something like that. So you keep calling the function. So from top level, that's program, keep calling different function. Okay. If it fail, you go back. If somehow you fail, you go back and try second choice. If second choice doesn't work, you try third choice. If third choice still doesn't work, then the grammar fail. Okay. So this is LL passing. So LL parser, you can hardcore it. You can write a program by yourself without the code generator. This is a parser, okay? Based on if your grammar write well, your parser should be done pretty soon, okay? So LL parsing is always predictive, and it actually is when the language compilation is easy. LL parser can write a parser in a very short time. Okay. So we have read A, read B, sum equals A plus B, write sum, and write sum divided by 2. This actually is one program, okay, for average program. So this average program, when you pass with LL parser, you'll be like this. This is the parsing tree. Okay. Any question? So this one means that you pass this language as in this program as input to this parser, to this LR parser, and then using the recursive descent algorithm, and you create such a tree. Is that okay? Any question? Any question? Okay, let's do this. Okay, so today may be a little bit longer. Okay, let's have a 70 minutes break. Let's come back on 11:10. Okay, I think we are half the way today. I'm sorry, your time should be
Oh, yeah.
1:10. Okay, sorry. Your time should be 1:10. My time is this. Okay, your time. Let's break to that. Okay, today is a little bit longer. Okay, break.
All righty.
Okay, I'm back. Okay. Any questions so far? Okay, if no question, let me actually let's resume. Okay. So this is a recursive descent. It's very simple. Okay, recursive descent parsing. Is very straightforward. Okay, let's assume that we have a monkey language. So a sentence is defined as subject, verb, object. Okay. So subject defined as a person or monkey, right? A person or monkey. And verb can be defined with love or hate. Object can be me or you. Okay, this is a so-called monkey language. Okay, it's very simple. So let's assume that we do write actually person hate you. This is legal because you actually the first word is a person. You try this one and it actually okay, and then verb, and you would go try verb because you see the hate. So try love, you fail, go back, and you try hate. Yes, you pass, right? And then you move on to the next one. You see you actually you try me, fail, go back, try you, pass, and that actually is very straightforward. Okay, so based on this monkey language, this recursive descent will pass. Okay, so let's try another one. Okay, so let's try another one here. Let's try monkey hit you. Okay, so first one, try person fail, try monkey pass, okay? And then so there's a subject, you pass, go back. And then you will try hit. Hit you try love, fail, try hate, fail. So this one you will report error in the grammar. Is that okay? Is that okay? So this is pretty simple. So gradient descent just what try you have your grammar and you try your leftmost non-terminal first. Keep doing that recursively. And if you pass, it pass. If it doesn't pass, it doesn't pass. Okay, so very straightforward to do that. And they are also recursive descent, and you can come with tool. Okay, you can use tool. Okay. So this is a calculated the P1, okay, and you use a parser lexer to build it. So here we building a lexer, and we are using what pre. Okay, last week we talked about pre. So we use the grammar we put there, and then you create a lexical analyzer. Okay, and then we can build a parser based on the grammar. So these are the rules. Okay, these are the rules for the grammar. Okay. So when you write into the pre and you will create a parser by yourself. Okay. You create parser by yourself. And there are some error terms, there are more complicated error terms. But anyway, it will create a parser. Okay. And you can run the parser. Okay. So you can try. Okay. And the next one we are going to talk about grammar for LL1. So grammar for LL1, you do have, you have to avoid the leftmost recursion. You also need to guard against the left factorization. These are wrong. These are also wrong. Okay. These two things cannot happen on LL1 passing. So let's look at the first one, elimination of the left recursion. So left recursion happens when you have a grammatical union and it calls itself by itself, and you create recursive call, because every time you call this one, you call it by itself, okay? Because this is a definition for the recursive descent. If this happens, your program never ends, okay? So this one, to actually get rid of this, you can adjust left recursion to right recursion. So with this one, your left recursion problem will become, okay? So this one okay for LL parser, this one no, okay? So let's look at it. You have ID, comma, okay? You have to change it to comma ID. So first one, the ID, followed by comma ID. This is okay for left recursion. This one, no. This one, if you say ID, comma, this one, you actually will go into the recursive code right away. Is that okay? But two grammar will deliver the same result, but only right-hand side can survive with a recursive descent type of LL parser. Okay, is that okay? So we change the grammar from left side to right side. Okay, that's actually called, that actually is the first problem we try to avoid. That actually is the elimination of read recursion. We have another problem called left factorization. Okay, let's look at the left factorization. It's called common prefix. So here, if you have equal ID equals expression or ID parentheses arguments, then you have problem of, hey, I do have ID on the first element, but I don't know I should call this one or call this one. Okay, so this is called common prefix problem. This is also not okay in the LL parser. Okay, to solve it, you create a different rule. So your statement equals ID followed by statement tail. So by doing that, you kind of factor out. It's just like AB plus AC. You kind of take the A out. It's okay. It's called common factor. So your A derive AB and A derive AC. Then you can do A derive A with the non-terminal B, and B can be B or C. Is that okay? This is the so common factor, left factorization. You don't allow such a rule, you actually factor it out. Then this is okay for LL parser. Is that okay? That is make sense.
You said the capital B is a non-terminal B?
Capital always means non-terminal, yes.
Okay.
It means that it can be derived by other terms. Terminal means A or 3. You don't go recursive descent lower. Is that okay?
Mhm.
A B, you will try BC. This B is a non-terminal. You try B or C. Okay. Any question? Okay, so this one, so these two things are something that you need to handle. One is elimination of left recursion. Another one is the common the factorization. Okay, these two. And then passing will have some trouble with the dangling else. Okay, so dangling else will happen when you have the if else statement, but you have to judge the else statement. Usually we will actually have it stay with the closer if. Okay, so if you have if it's condition 1, then if condition 2, then S1 else S2. Usually we will say this else belonging to the closer if, not the further away if. Okay. Okay, this is called dangling if. Okay, so we will also try to remove dangling else by using the grammar to determine it. Okay, so this is actually when you have this set of grammar, it will handle this dangling if. Okay, dangling else. I'm sorry. Okay, so you remove of the ambiguity in the grammar. That's very important. When you design the grammar, you need to handle it. Okay, so there's also one way that you can handle it, is that you do use an and. Okay, some language prefer it to use an and for the dangling. So there is possible you write if A this, else this, okay. And you can use and. But the problem is that if you have too many labels, you end up with so many and. So in Python, it's more like this way. Okay, more like this way. Python is more like this way. It's not the same, not exactly the same, but more like this way. It's if, L if, L if, L if, else. Okay. Any question? So to avoid ambiguity, you can write this way or this way. Okay. And usually nowadays, the modern language using this way. Okay. LL passing, okay, and you can use a table-driven type, okay. So you can use a table-driven type if you have the grammar rule in the passing table like this, okay. So you can pass the table using the grammar. Okay, so it's called table-driven parser, okay. And this table-driven parser will be, the algorithm will be like this, okay. you would call the table and generate it. So this is the dual generation table. Okay, this is dual generation. But this one is not easy to understand so far. Okay, let's look at the example. Okay, it eventually will pass the language into a tree like this. But let's look at the next one. Let's look at the LL passing. Let's look at the rules. Okay, using to build a predict tree. Okay, so this predict set is used in the compiler. Here you have this predict table. Okay, and that would actually help you to build a table like this, and then later performing the passing like this. Okay, but before we do that, let's look at this different predict tree. Okay, predict set. So predict set actually, to build predict set for a calculated language, there are 3 stages. Okay, you build a first set, follow set, and a predict set. Okay, so usually we will build 3 sets: first step, follow set, and predict set. Okay, so let's see. So the first step, follow set, and predict set. Okay. Okay, so what does this means then? Okay. So let's look at the predict set. Okay. So predict set is that you do see the grammar with A followed by a token. Okay. So if we see A and it's starting with a token, so A's predict set would add with the token. Is that okay? So that means that you do see A, but very likely you will start with a token. So token is a predict set of the A rule. Is that okay? So if A is actually generating a B, and then B's predict set would be included by the A's predict set. Okay. And the A will generate empty symbol, then the follow set of the A will be the predict set of A. What does this mean? This actually means that, okay, A just done, but A may be followed by some other symbol, and this one will be its predict set. Okay. So these are the rules that you actually, based on your grammar rule, to create your predict set. Same thing, you will have the grammar rule that will actually show you the predict set means the set of the symbol that will happen when you generate by the rule. Follow set means that you have this symbol and what token will be following.
Predict means it must be that way.
Predict means that going lower to the next level of the grammar. Follow means that the token will follow it. Is that okay?
Mm-hmm.
So let's see the example. So if here we have a calculator language like this, okay, and let's actually build a predict set for this calculator language. Okay, so first thing is you do a non-terminal starting symbol followed by a expression then stop. Okay, so initially you put a dollar sign over there and construct the empty symbol set. Okay, we use the rule number 1, and empty symbol set would be expression tail with terminal tail. So we build that, and then actually we create a predict set. Okay, so predict set is like your expression tail will have operator A, terminal tail will have operator multiply. Okay, so this one is based on the rule of the predict set. This one is based on the applying rule number 1 for predict set. Okay, let's go back to the rule number 1 for predict set.
Because the operator will be before the tail.
It will be the first element of the tail. So this is a rule that actually we go back to the pretty set. If the token followed by token would be this one. Is that okay? Pretty set of A. So that's the pretty rule number one. So when you go here, we say pretty rule number one that actually is doing that. The operand of that is the pretty set for you. Okay, and then here we actually do look at the follow set here. Follow set here is the expression. This one expression is the terminal with the terminal tail, right? So you have expression followed by a stop symbol. So the stop symbol and the right hand side parenthesis. This is the right hand side parenthesis. These are the follow set for expression. So that means that your expression may follow by a follow set, or expression may be followed by the stop of the program. Is that okay? This is the follow set. So follow set are the symbol that actually would be following the expression. The symbol pretty set is the symbol that actually will be generating by the rule and part of your code. Okay. So this by doing this, we generate a follow set. And there are several rules you actually can generate a pretty set. So we keep doing that to generate a pretty set and follow set. You will have a complete design for a pretty set and follow set. And based on this pretty set and follow set, we go to pass our calculator language. Okay, so you create a pretty set and follow set by doing this. Okay, first set, follow set, pretty set. And then using that to pass your tree. Using that to pass your tree, and eventually you will get follow this one, and eventually you will get the whole grammar done, and you will use that to create your passing tree. You do one by one of rule, you will generate this. Is that okay? Okay, that's called LL parsing. Okay, that's a systematical way of doing LL parsing. Then we have another one that's called LR parsing. LR parsing is actually different parsing. They have different grammar, and they kind of not using the recursive descent. It is using the step and do table driven. Okay, so you actually have the action and goal. You have a token input, and you will push some grammar unit to the stack, and there's a shift, reduce, and go to table. Okay, so that's usually the LR parser is. So basically, you need to have a pre-compiled table. This table is the action and the go-to table. So LR parser and the LL table-driven parser similar, but using different table. Is that okay? Similar, but using different table. And different language, different grammar will end up with different action and go-to table. Okay. Okay, that's also used for table-driven, and the algorithm is right here. How the table-driven can be done to generate a symbol is in this algorithm. It's called LR parser driver. Okay. So we create some table like this, and that is used for the LR parsing. Okay. And then you do one by one with the input. Right here, we do one by one with the input and the action and go to deliberation, okay? So this one can be used to pass in the whole thing one by one, go one by one, and you get the passing stages and action that you take here. And this is a stack condition, okay? So this one will pass the whole input of A times B plus C, okay? And the whole A times B plus C will be passed based on the table. It will be like this, okay? Okay, so here we do have an example for the canonical derivation, okay, step by step to do parsing using the LR parser, okay. And you can model it, okay. So basically here also talk about how is the statement being called, okay, and how the stack work. And this is the grammar that actually eventually being driven using the table, okay. And you create a finite configuration finite state machine, okay. Characteristic of finite state machine, okay. You generate something that is, and then that it will be a table that is for us parser, SSL, XLR parser. And the dual will be like this. So basically that's the table-driven SAL parser, okay. Anyway, so here we finish the two type of parser and its design, okay. And every single one take a long time for you to study, but please try to look at them, okay.
Why is it in a stack?
Hmm?
Why is it in a stack?
Why is there is a stack? You will push the turn and some value to the stack. When you use the SLR, when you use the LR parser, you will keep doing that.
Pushing the grammar into the stack?
Grammar is in the stack, yes.
And then how do you pop it out?
You pop it out when it matches some certain rule.
Okay.
You pop it out when you send it. So when you match certain rule, you pop out with T. These three will be pop out and generate a T. They call it reduce. When you do reduce, it actually is something like that. Okay. So this one is just to tell you a systematical way of handling the ship reduce fiber. Okay. The algorithms right here. And the detail, you have to go through this example once before you can fully understand how this ship return to. Okay. But it takes a long time, maybe 1 hour to do that. Okay. Okay, so I think today I'm up to here, okay? And the things that you need to go through the table driven by yourself at least once, okay? And you need to go through the recursive descent at least once to understand it, okay? Otherwise, all of these take a long time to understand. And this is set and this one is generally for LR parser by using table. You also need to go through the whole creation of preset and creation of the follow set one by one, okay? Going back to trace back. So using this example and my rule for the prediction, you will see that it actually is there's a one-to-one mapping, but it takes a long time to for you to really understand how you build up the PD set and the follow set, and how the PD set and the follow set can be used when you do table-driven parsing for the compiler. Is that okay? It takes some time to do it. Okay. Any question? Okay, if no question, we're up to here today. Okay, thank you. See you next time. Bye bye.
Thank you.
Bye bye.
Hi, I actually wanted to talk about my project.
Yeah, you put your question about your project.
Yeah. So I didn't get any like specific feedback. I just you just wrote that it's not exactly like a good topic.
The
so-
feedback, okay, project I've been talking about it million times. It is a creative project, so we do not give you idea of which one you should do or you should not do. But there's only one guideline. Whatever project you want to do must be related to programming language. You must do some kind of translation. That's only one guideline we have for you.
Yeah,
Is that
but my
okay?
my
Yeah.
topic was like related to programming translation.
Then that's
I
fine.
just didn't-
Then that's fine.
But you said that it wasn't a good topic in the comments, and that's all.
Yeah,
good
that
feedback
means that
was.
that means that I evaluated it is not a good project. I actually grade on it, and if I say that's not a good project, that means it's not related to programming language.
So are we allowed to change our topic?
Yes, you are allowed to change your topic.
Do you want us to?
The proposal and the term project do not have to be the same project. We talk about it in day one.
Okay.
So basically, in the middle, you switch project. That's fine. That's acceptable.
Okay. Do you want us to like confirm our topic again with you if we are changing it?
Any project is acceptable. In the middle, you can change the topic. So if you want me to look at it, okay, you can send me another version of your new topic. But usually we want students to handle it by themselves. So translation, what is translation? Translation, we teach you the whole semester on it, right?
Mm-hmm.
How you use a parser, how you use the scanner to do translation, right?
Yep.
That's the goal. Other than that, we don't have guideline. And we give you three possible candidate projects, but you do not need to pick them if you don't like. You can pick any language or any example, a project that you like, as long as there is a language translation.
Okay.
So
Well,
one example is that there is a student in the meeting I talked about it before. It's like he picked the Morse code translation to English, and that is acceptable. That is acceptable. So you just need to find one of the translation, no matter what language, American Sign Language, right? Whatever you can find, as long as there is a translation, that's fine. And whatever you have done in the proposal, if not appropriate, it's okay. You can change the project. And what project, I don't know. You have to find it. It is a creative project. So we allow you to find whatever project you like.
no, that's fine. I totally understand that it's something we're supposed to choose ourselves, but I was just confused about the feedback I got. The topic I chose.
That means that the topic you pick is not related to programming language.
I mean, mine was like translating a Python program to micro processor assembly language. I didn't understand how that's not related to translation.
I have to look at it one more time. If it is translating Python to micro what?
To assembly language.
Then that's fine. If you translate Python to assembly language, that's fine. But I do not read it in your report, okay?
Sorry?
I don't get it in your report. I don't get it in your report. You
didn't understand what I was talking about.
I don't know what you were talking about. Yes.
Okay. I guess I wasn't clear. Okay, if you were okay with that,
You
that's all I
don't
wanted to make
make it.
sure.
You don't make it clear, so that's why I told you that it's not appropriate.
Okay.
But if you are not, if you are sure that you are doing Python translated to assembly, that actually
Yes.
it will be acceptable. Yes.
Okay. Thank you so much. I
Is that
just
okay?
wanted to make it clear.
Okay, but as long as you do the translation, we are fine. Okay.
Mhm.
And changing topic is also allowed.
Okay. Thank you.
Okay, if you don't like it, eventually for some reason, you don't have time to do it or whatever, you don't like it, you want to change the
Yes.
topic, that's also allowed. Okay.
Okay.
Any more questions? No? Okay, no, thank you for coming today. Okay, thank you. Bye now.